So as an extension, let's see how does partial derivatives behave when we have certain constraints for the variables. Right, so let's discuss in detail. So the keyword here is constraint. So what is constraint? What is the literal meaning of constraint? Something controlling something, right? So let's examine what is that and what is controlling what. So suppose we have a function w, say f of x, y, z. Right. We have seen that, or we have learned that in such an expression w may be called a dependent variable and x, y, z may be called as independent variables. Right. This is valid unless we have another equation connecting x, y and z simultaneously. Which means if we have a new expression, say for example z equal to x square plus y square along with this function, then x, y, z may not be purely independent always. See, z, say z z is actually depending on x square and y square, or to be simpler, x depends on x and y. So z is no more an independent variable, but z is a dependent variable of x and y. This can be restructured to see that x square equal to z, y square minus z, which implies x equal to root of y square minus z. So x actually depends on y and z. Similarly, we can derive an expression for y square and thus y from this equation, which we can use to deduce that y is depending on x and z. So what is happening here? So all these three are dependent variables, no way. Right, there should be something independent. Right, so these are actually different cases. We choose one of them. We choose one of x, y, z to be a dependent variable and the other two to be independent variables. Right, we make the choice, and the crux of this session is to examine how does the partial derivatives and the geometrical meaning of them change with respect to our choice of dependent and independent variables. Right, so what are we going to do now? We'll examine certain cases like this. We'll try to find the dependent variables and independent variables. We'll examine how do they change the partial derivatives and their geometrical meaning. Right, so this can be better explained using an example. Such an equation connecting x and y other than this function may be sometimes called a constraint. Right, so hope the things are clear so far. So let's move to an example where we can make things clear. So consider we have a function w equal to x square plus y square plus z square, and we have a constraint, say the same one we have used before, z equal to x square plus y square. Right, so we have a function of x, y and z, and we have another constraint connecting z, x and y, say z equal to x square plus y square. So if we haven't had this constraint, this is purely the case where w is an independent variable, w is a dependent variable, x, y and z are independent variables. But as we have another constraint, that may not be the case. Right, so let's make the choice of dependent and independent variables here. The question is not yet complete. The question is to find dou w by dou x. We draw something from the question that we are asked to find the partial derivative of w with respect to x. So far we have been finding partial derivatives with respect to the independent variables, right? So relying on that custom, we choose x to be an independent variable. Remember, this is purely our choice. We make the choice, right? So x is chosen to be an independent variable. And what about w? Can w be a dependent variable or an independent variable? No way. However, w depends on x, y and z explicitly. So w has to be a dependent variable. Right. So I'll write it in another fashion. We have certain possibilities, so let's tabulate them. So dependent and independent. Right. W has to be a dependent variable and X has to be an independent variable. Right. And we have the constraint Z equal to X square plus Y square. Right. So Z is actually depending on X and Y. So Z is a dependent variable, and obviously for that reason Y has to be an independent variable, since we does not consider the equation Y square equal to Z minus X square here. We do not consider that. We just consider Z as a function of X and Y, not Y as a function of Z and X. Right. So this is a possibility. So is there any other possibilities? Yeah, of course we can consider this equation now. So as per that equation, however, W is going to be a dependent variable since it depends on X, Y and Z explicitly. And if we consider Y square equal to Z minus X square, which has come from the same constraint, you may derive that Y equal to root of Z minus X square or Z minus X square all raised to half, which in some sense says that Y is actually depending on Z and X. So Y has become now a dependent variable. Right, and the other two, X is considered as independent since we are actually trying to find the partial derivative with respect to X, and the other variable Z is independent in this case. Right, is there any other possibility? The possibilities arise when we rearrange the terms in this constraint. For now, we don't write X square equal to Z minus Y square, and we don't express X as a function of Y and Z here, since we for the sake of question we consider X to be an independent variable. Right. So for this case, for this situation, we have two cases. In case 1, W and Z appear as dependent variable. X and Y are considered to be independent variables. In the second case, W and Y are considered to be the dependent variables. X and Z are considered to be the independent variables. Remember, we made these choices. You have the freedom to choose case 1 or case 2 unless it is specified. Right, unless the independent variable and dependent variable are specified, you have the freedom to choose in between case 1 and 2. Right. So now we have seen that we have two cases, and the key question is, how does the partial derivative dou W by dou X depend on these cases? Does it gonna change? Or is that going to be a constant over these? Constant in the sense, an invariant. What we mean by an invariant is something which does not change with respect to the change of cases. Let's examine. Let's take each case and find dou W by dou X. So the strategy is to consider each cases independently and examine what happens to dou W by dou X. Right. So I hope you people remember this. I just have to clear this as we have a serious shortage of space. So right. So what was the case 1? What was the first case? The dependent variables were W and Z. So remember the expression W equal to X square plus Y square plus Z square, and Z equal to X square plus Y square. Right. So now we have Z to be a dependent variable which depends on X square plus Y square. Right. So yeah, we can substitute this expression for the Z in this expression for the function or the value W. Right. What we will get? W equal to X square plus Y square plus Z is X square plus Y square. So Z square is X square plus Y square all square, which is X square plus Y square plus X raised to 4 plus 2X square Y square plus Y raised to the power 4. Which is a simple expansion of A plus B whole square. Right. So what is this? X raised to 4 plus Y raised to 4 plus X square plus Y square plus 2X square Y square. Now we can find dou w by dou x. Simply differentiating this with respect to x, keeping y as a constant. Right. So what will we get? 4x cube plus 0 plus 2x plus 4y square x, isn't it? Which means 4x cube plus 4y square x plus 2x. Okay, so remember this value, note it down please. Dou w by dou x gives the value 4x cube plus 4y square x plus 2x. Right, now let's move to the case 2. So now what is case 2? Case 2 we had w and y has the dependent variables, x, z were the independent variables. So the constraint was actually z equal to x square plus y square, and since y is considered as a dependent variable, we use y square equal to z minus x square. Right, we have the function w equal to x square plus y square plus z squared. Now we can replace this expression for y square here, which is x square plus z minus x square plus z square. So this x square and this x square may be cancelled out as they have opposite signs. So what is left out here? Z plus z square. So what is dou w by dou x? Clearly this is truly independent of x, which means dou w by dou x is 0. Right. So when we had the first choice, we got this expression for dou w by dou x, and when we moved on with second choice of selection of independent and dependent variables, we ended up at a different answer for dou w by dou x. So what does this mean? Partial derivatives change with respect to the choice of dependent and independent variables. This may seem or maybe seem simpler, but this is something important which is widely used in applied mathematics for optimization concepts, which we may incur later. Right. So for now, remember that the partial derivatives may change their values according to the choice of dependent and independent variables. Right. This is very important. So we need to find move to an example. Consider w equal to x square plus y square plus z square with a constraint z equal to or another form z cube minus xy plus yz plus y cube equal to 1. Right. Find dou w by dou x at 2 minus 1, 1. So what is the case here? This is quite similar to the previous one. We have a function, we have a constraint, and we need to find dou w by dou x. So we have to make choices of dependent and independent variable. And for that reason, this question is considered to be incomplete. Right. Sometimes we restrict our questions to have a single answer, but this question may have different answers with respect to different choices of dependent and independent variables. Right, so this question may be considered as incomplete, and to make this question complete, you may ask for a certain choice of independent and dependent variables. So let's fix a choice here. Suppose x and y are the independent variables. Right, x and y are the independent variables, and that itself gives us the information that w and z are going to be the dependent variables. Right, so this question is now complete. We have a function, we have a constraint, we have to find dou w by dou x at 2 minus 1, 1 when x and y are considered to be independent variables. Right, so you can try to solve this, but there is a slight difference from the methodology used here. Let's try to solve this now itself. Instead of simply substituting the expression for any variable into the function, let's start with differentiating this expression implicitly. Right. So what is dou w by dou x? Dou w by dou x, which is equal to 2x plus x and y are considered to be independent variables. So y does not depend on x. So when we differentiate with respect to x, y, which is something independent of x, will have the derivative 0. Plus z is a dependent variable, which means z may depend on x. So the partial derivative of z square with respect to w will be 2z into dou z by dou x. Right. Now use the second expression of the constraint to find dou z by dou x. Conduct the implicit differentiation with respect to z on the constraint. So dou z, so let's consider 3z square into dou z by dou x into dou z by dou x minus y is an independent variable, so y does not depend on x, it may act as a constant, so minus y plus y is again a constant, z may depend on x, so dou z by dou x, since we have considered z as a dependent variable, plus y cube is again a constant since y is an independent variable, which is in terms 0. Right. So constant 0. So can you solve for dou z by dou x from this equation? Pretty simple. Dou z by dou x will be y by y plus 3z square. Right, so you got the expression for dou z by dou x and fix that expression in this. Two x plus 2z into y by y plus 3z square. So this gives the value or the expression for dou w by dou x. So what we have done now, we just simply differentiated both, and we have used the technique of implicit differentiation, and we found the value of dou z by dou x from the constraint and simply plugged into the dou w by dou x obtained from the function. Right, it's pretty that simple. There are a few more examples available in your textbooks. You may refer them and try to solve them out.